Hey everybody, good night or good morning, whatever time it is that you are looking at this video. I know that there's quite a bit of information we're sending out to the class because it's an online class basically, and I'm not intending to record every single PowerPoint that I show you guys, but I think there's a few things in particular I wanted to emphasize as to highlight certain aspects, certain parts of the presentations, and here is one of them that I want you to pay attention to very carefully. I sent an announcement about the new PowerPoint available on Monday, and I'm sending out another one later tonight, Monday night into Tuesday morning, so be aware, be advised, check that out. Anyways, here is a look at the world around us, which is amazing. And I hope to give you guys websites so you can look at this in your own time. Here's a phenomenal high resolution satellite imagery that gives us a shot of planet Earth that it took very many years for most of the public to be aware of. Satellites going up and taking snapshots. You can see the sun is setting and the darkness is covering from east to west. It's an obvious rule of geography there. Now, earlier on Monday, I looked at some very interesting information from 160 years ago, and that was a day that a very intense, a extremely impressive heat wave basically baked Southern California. It got up to unofficially 133 degrees in Santa Barbara, which is something just insane. And there's a lot of explanation for how that could be possible, if those are accurate readings or not. I sent you guys the info that you should have hopefully looked at, or if not, check that out. Anyways, the question is, how can this even occur meteorologically? The first thing we have to realize is the atmosphere has structure to it, and there are actually layers to the atmosphere. Now, the first layer is what we call the troposphere, and this is the weather layer. It extends from about the surface of the Earth on up. At the equator, it's thicker. At the poles, it's thinner. And the reason for that is due to the thermal expansion of the atmosphere. As the atmosphere is hotter, it gets basically thicker. As it gets colder, it gets thinner. And you see this happening at the poles where it's about half the depth of the equator. And this fluctuates during the seasons. In the winter time, the troposphere actually gets a little bit narrower. In the summertime, it expands and bulges out. And this is a phenomenal rule of the Earth's atmosphere, which is phenomenal and interesting, and you can learn more about it on your own time. But right now, I want to focus on the layers. You don't see this with your eyes, but you recognize this with instrumentation. Every several thousands or tens of thousands of feet, the atmosphere goes through a different property. It gets colder in the first layer as you go up in height. It gets hotter in the next layer, colder in the next layer, hotter in the next layer, and there's more where that came from. And so we're going to focus right now on the troposphere. The reason for that is because our question is, how can it get so warm and how can it get so cold, and how can the weather change, and is that normal or not? So bear with me. We hope to address that right now. So, for lack of a better phrase, contrary to popular belief, many times when we learn about the atmosphere, the principles of weather, of meteorology, of climate, of climatology, we start to come across ideas that maybe are not well known by most of society that doesn't study them. One of these ideas is how air heats up and how air cools down. Now, getting into all the complicated parts of it, it's going to take us into the other chapters of our book. We're not quite there yet. But simply speaking, the atmosphere is made up of a lot of gases: nitrogen, oxygen, water vapor, carbon dioxide. Some of them have a lot more and others have a lot less. And there's fluctuations, ratios. But the main reason for the warming or the cooling of our atmosphere is not necessarily concentration of the gases. It's the pressurization of that atmosphere as it relates to the Earth underneath it. What do I mean by that? This is a principle called the adiabatic cooling or warming. And simply speaking, it works kind of like this. As air rises, it goes up, it expands due to a gas law. We hope to learn about that later on. And as air expands, it cools because the molecules are going to be having a lot more room to roam. And when molecules are able to have more room to move, they're not all squished in together. And as a result of not being squished together, there's less friction applied, and less friction leads to less heat. Now, that's why as air is lifted up, it expands like a balloon, gets more and more and more in size, and the molecules have more room to move around. And therefore, there's less pressure that is a result of the molecules having much more room to breathe, if you will. Not really literally, but you get the idea. And the reverse happens when the molecules are squished in together when air descends. As air descends, it actually gets from a larger space to a smaller space, from more room to less room. The molecules are going to be pushed more together. They're going to have more impacts. They're going to have more friction. Friction leads to heat. And therefore, the rule is as follows. As air goes up, it expands, it cools, and the pressure on it is lessened. As air goes down, it compresses, it warms, it heats, the pressure is increased on it, and guess what? It gets hotter. And this is a very important principle to keep in mind, because whenever you work with a tire pump, for example, and you want to go ahead and put in air into your tire, if you do this experiment, you take a bunch of air that comes in from a very large volume, and you compress it into a smaller space. That is essentially this principle in action. As the air is compressed, it heats up, and the temperature of that air will usually be quite a bit warmer or hotter due to this occurrence. Now, this is something really important that we have to try to wrap our minds around to understand how air warms and how air cools, and it's really important for meteorology. So remember about a week ago or so we had that heat wave, several days of really hot weather, which actually, if you looked at any other years before this one, it wouldn't be that unusual because, well, it gets hot in the summer, except the last about 6, 7, 8 months have been generally cooler to much colder than normal around here. So when it actually got hot, it felt a lot more unusual because we've been used to the cool weather. And guess what? It's back to cool. So how do you explain that? How did it go to be really hot all of a sudden and to just cool back down? The answer is when it got really hot, the air compressed. Why did it do that? Because the atmosphere isn't equally configured on Earth everywhere. It's always doing different things at different places, and it's moving around. Some places have thicker atmosphere, some places have thinner atmosphere, and some places the troposphere has more depth to it, other places it has less depth to it. So whenever the atmosphere, particularly in the summertime, is getting hotter, it's basically generally a result of the compression effect of that atmosphere. The pressure is increased and the temperature is going to be on the way up. And you can obviously understand and infer from that the opposite, that when the pressure is decreased, the atmosphere may start to respond by getting cooler. And hence, that's what is occurring these last several days. I don't think anybody's complaining, but some people do want to go to the beach and do want to hang out by the poolside. You might have to wait for that, though. So what happened 160 years ago that caused that brutal heat episode to occur, and again another one back in 1917 that lasted for several days? The short answer is the atmosphere had major compressional heating. And due to the compressional heating and some other configurations that took place, it got really hot. And it broke records that have been staying and standing to this day in parts of Southern California. Now, how does the weather look like out there closer to home and closer to now? Well, here's a look at the National Weather Service. And this is a homepage. You can go on to it, www.weather.gov. And this is the branch of the federal government that has forecasters, meteorologists working 24/7, 365, monitoring the nation's weather. Now, when the weather's active, you get all sorts of colors like you have in parts of the country today. When the weather's quieter, it's basically blank. Let's take a look at Southern California, where it's not very active right now, although you can argue in June it's usually a quieter part of the year. Anyways, we can scroll on and zoom in onto Los Angeles. Let's take a look at the conditions in Santa Barbara that occurred on your Monday. And here's a hint. They were nowhere near as hot as they were back in the 1800s, to be obviously not understated. What happened? Let's take a look at the observations. Let's take a look at that. You can go ahead and zoom in on the data, the observations that we have. It's pretty cool to be able to see this. and you can just go ahead and cruise on through. All these little stations are actually weather stations, and you can zoom into your neighborhood. Obviously, most of you guys do not live in Santa Barbara County, but you might visit there. If you do, it's a nice time of year to do that, provided it's not 100 and something degrees, which obviously doesn't usually happen every day or even every year, for that matter. Here are the stations around Santa Barbara. Let's take a look at some of them that are the closest ones to probably those readings that we saw historically. And obviously we know stations come and stations go. Here's one right at the coast where the temperatures at this hour, I'm recording this about a little after midnight, is in the low 60s. And you can see generally temperatures are comfortable if you have a jacket or sweater on hand, right? And typically speaking, the water temperatures are not that much warmer than the air temperatures here at this time. So obviously wetsuit time if you're going to be going to the surf, right? For sure, unless you're a hardy soul can deal with that. So what was the temperature like earlier on your Monday? Let's take a look at that by clicking on one of these observations, going to the 3-day look. And that 3-day look shows us that the high temperature, which is the peak reading that was registered earlier on Monday, took place probably during the mid to late afternoon hours. You can see it right there on the left. And the temperature basically stayed well below 70. It probably maxed out right there in the mid to upper 60s. So unlike June 17th, 1859, when it was 133 unofficially, or definitely well above 100 to say the least, and like June 17th, 1917, 17th, 1819, it was actually about 40 to 60 something degrees cooler in 2019. And obviously, that is not necessary to be repeated. Okay, have a great night. Check this out. Look at the slides, and hopefully see you guys, or at least hopefully talk to you guys later on.